Alright, our first video for this particular lesson is going to cover Einstein's famous equation E equals mc squared. And before I get started, just to make sure that I am all set here. I think I am. Alright, so we're basically in your notes. We're on page 4 of your notes. And we're going to be right at the very top, pretty much, where it says video number 1, as it says right up here. So here we go. We're going to go ahead and start with the first bullet point, or first concept here, and just fill these in as we go along. So it says, up to this point, we have talked about the law of conservation of energy, which states that energy can never be, and here's your first two blanks, created or destroyed. Okay, so what does that mean? It means what we basically, up till 1916, scientists in the scientific community said that energy can never be created or destroyed. Whatever the energy you have, that's what you got. You'll never have any more, you'll never have any less. It can switch from one form to the other, but the total at the beginning and the total at the end will never change. Okay, the next one says this. Although we haven't talked directly about the law of conservation of mass, we have indirectly stated that mass can never be, and here it is, we've said that mass can never be created or destroyed. So just like energy that can never be created or destroyed, mass can never be created or destroyed. Alright, and then what we said just a moment ago, in 1916, Albert Einstein developed what's called the general theory of relativity. Now I'll just take a quick little commercial here. There's actually two pieces to the theory of relativity. There's what's called the special theory of relativity, and then what's called the general theory of relativity. And we're not going to go into the special theory of relativity. I'm just making a point that really the theory of relativity is broken into two pieces, special and general. And the general theory of relativity is what we're going to talk about right here. And it says that energy and mass can be created or destroyed. And that's different. That's like total reverse of what was thought before 1916. And in 1916, Einstein came out and said, hey, scientific community, you've had it all wrong. Actually, we can create and we can destroy energy, and we can create and we can destroy mass. And when you destroy, here's the next bullet point, and when mass is destroyed, energy is created. And when energy is destroyed, mass is created. You can literally destroy mass, and if you destroy mass, out of that destroyed mass, you create energy. And if you destroy energy, out of that destroyed energy, you create mass. So after Einstein developed what's called the general theory of relativity, the law of conservation of energy and the law of conservation of mass were combined. Those two laws that we talked about earlier, he put together. And he put them together into one new law, and we call that law the law of conservation of mass energy. And that says that mass and energy can be, here's the next two blanks, created and or destroyed. And when one is destroyed, the other is created. You can think of it this way. You can think of mass and energy as two sides of the same coin. If you have one, this is the next bullet point, if you have one, you really have the other. Trying to think of another analogy. I can't think of one right now. That's the best analogy. If you have one, you have the other. If you have mass, you really have energy. And if you have energy, you have mass. Because if you have one, you can destroy and create the other. That's the way you want to think about it. So, number 5. The law of conservation of mass energy can be described mathematically as, and there's the equation, E equals mc squared. That equation right there, E equals mc squared, sums up everything that we put together right up here. That's the value of that equation. Now we're going to take a look at that equation. We're going to flip the page and see what that equation actually says, because we're going to use it in this unit. So what does the E stand for? You probably already know that E stands for energy and is typically measured in joules. Now we are going to change that a little later on, but for now that's perfectly fine. And you know that J is joules. M represents mass. You probably figured that out. And is typically measured in kilograms. And that's vital. That's really important that you have it in kilograms and not grams, because that'll screw everything up. And then C, you probably know this, is the speed of light. Okay, now here's a real important fact. When you use E equals mc squared, the speed of light must be in meters per second. You got to have it in meters per second, because that'll make the units for energy turn out to be joules, and that's vital. The E in E equals mc squared represents the amount of energy that is created when a certain amount of mass m is destroyed. So that equation can be used to calculate how much energy is created when you destroy mass, and it actually can be used to go the other way. You can use it to determine or calculate how much mass is created when you destroy a certain amount of energy. So here's the next bullet point. The mass in E equals mc squared represents the amount of mass that is created when a certain amount of energy is destroyed. Alright, so let's do an example. We're going to calculate the energy equivalent, that's kind of the fancy way of saying this, or the amount of energy that is created if a baseball is completely destroyed and converted into energy. Alright, so what does that mean? Well, here's the first problem. I didn't think about this. I thought I was going to be talking to a classroom full of Cardinal fans, and they would have a very good understanding of what a baseball is. But I know that we have a couple Cub fans in the audience, and they're not going to understand what a baseball is. So instead of a baseball, let's use a tennis ball. And so here's the concept. That way we can include everybody. We don't want to leave anybody out. So if we were to completely destroy this tennis ball, like poof, snap of my fingers, the tennis ball's gone. Not like move to the side out of the frame, okay, because it still exists over there. There it is. Alright. When I say like poof, like it's gone, it doesn't exist anywhere. How much energy is produced when I do that? That's what's vital. That's what's important. And so to do that, we have to know its mass. And so I have a scale that I'm going to turn on. Here's my scale. I think I'll try to zoom out here a little bit so we can kind of see the scale. Here's the scale, and it's thinking right now. It's busy. It's measured in grams, and that's real important. There's my grams right there. I'm just going to put the tennis ball right on there, and the tennis ball has a mass of 56.9 grams. I'm just going to slide that to the side and record that. So the mass of my tennis ball, I'll go mass here, equals, what did we say, 56.9 grams. Now, here's the issue with this. I can't have it in grams. Okay, that's what we tried to say up here earlier. We've got to have that unit for mass in kilograms. So I'm going to simply convert. And I'm just going to convert like this. I know that there's 1,000 grams. I know that there's 1,000 grams in 1 kilogram. So I'm just in my calculator. I'm just going to simply take 56.9 and divide by 1,000. So when you see this 1,000 in the denominator, that means you divide 56.9 by 1,000, and you get, there it is. Okay, it shows up right there. Okay, and I'll go ahead and write that down. So it's going to be 0.0569 kilograms. Okay, now we'll use the equation. E equals mc squared. And this is kind of exciting. You're actually using this equation. You've heard about it, and now you're using it. Alright, so let's do the calculation. We know that the mass is, and I have to use kilograms, 0.0569 kilograms. Don't forget to use the units. And then we have to come up with the speed of light. Well, the speed of light, I'm just going to tell you right now, is 3 times 10 to the 8th meters per second. And that's going to be squared. I have to take a mental break here real quick and make sure I didn't forget to tell you something. Yeah, I think I've already told you that. If not, you have it now. And then I just go ahead and plug this stuff into my calculator. So I'll just go ahead and show the screen here so you can see it being entered. Now, to be honest with you, I always start with the stuff inside the parentheses that's going to be squared first. So anything that's squared, I do that first. So I'll just go ahead and enter in 3 times 10 to the 8th. I usually hit enter just to enter it, and then I just square it. And there it is. Square that answer. And there it is, 9 times 10 to the 16th. Okay? Now, if you didn't see that, if you need some help with that, when you go to do the problems on your own, you let me know. You just call me over, and I'll show you how to punch that into the calculator. And that's, okay, so this 9 times 10 to the 16th, that's what this is altogether. And we're just going to multiply it times that guy. So times 0.0569, and there it is. Hit enter, and there's my answer, 5.12. The E stands for the times 10 business, and the 15. So I'll say 5.12 times 10 to the 15th, and we measure energy in joules. So if I were to destroy a tennis ball, like completely destroy it, that's the amount of energy I would produce. And you can think of it the other way. If I want to create a tennis ball, kind of weird to think about, but theoretically possible. If I wanted to create a tennis ball, I'd need that much energy. If I had less than that energy, I would not be able to create the tennis ball. There's the end of video 1. Good luck on example number 3.